Now let us focus on the optimal mechanism design problem for multiple agents. We have seen the single agent problem before, and in this context we'll call this mechanism optimal if it is BIC and IIR and also maximizes this revenue. In the single agent problem, the notions of IC and IER were same both in Bayesian and non-Bayesian settings, but here we are going to focus only on the Bayesian setting. Now, in this module, we will actually see an assumption which is similar to the monotone hazard rate condition, actually weaker than the monotone hazard rate condition. And we will see that under that condition, we can actually maximize the revenue and we can give a very clean result. So by the previous results, this problem of maximizing revenue, this BIC and IIR, reduces to the fact that all these FIs are actually non-decreasing in expectation that we have proved in one of the previous modules. And also this pi-i-ti's has a very specific formula that we have discussed there, similar to the Meyerson's payment rule, with the additional constraint that the constant value pi-i0 should be equal to 0, because interim individual rationality will require this to be less than or equal to 0. And since we are trying to maximize the revenue, it must be equal to 0. All right. So then the expected payment made by agent I is a very similar expression. You have the payment for player I, and you are multiplying that with the probability of Ti taking this value. So this is the prior distribution over Ti, and we are taking the expectation with respect to that on the payment. So this capital Ti, just for reference, this is an interval between 0 and Bi. Now in a very similar earlier exercise, we can reduce this expression, and we are not going to show that in detail. It requires to change the order of the integration, and finally we get this WITI, which is the virtual valuation of player I, and that is given by this expression here. Now we also know that this alpha ITI has a integral formula. So because this is taking the integration, so this is a expected allocation of player I. That means it is expecting with respect to the other types of the other players. So this is, if expanded, this will be the expression for that. Now one can do a little bit of mix and match. So we have this GIT minus I, and this is GI. So together, if you take the product, this is the joint distribution over all TIs, even though they are independent here. They decompose into their products. And similarly, we can actually look at this Fi of TIT minus I, which can be written as T. So this together actually makes the complete integration over the whole of T. So just to remember that this T is not a single integral, it's multiple integral, because this D of T is actually dt1, dt2 up to dtn, how many players we have. And similarly, there will be n such integrals here. We are just compressing all this notation. So now we can write the total revenue. So this was the revenue generated by player I, the previous expression. Now if we want to find the total revenue generated by all players, then we just have to take the summation over all these players. And because the sum is over the players and the integral is with respect to the types, so we can actually exchange this order of integration and summation. And we have this sum here, which is the sum over the virtual valuations multiplied by the allocation probabilities of those players, summed over all these players. This expression taking the expectation with respect to the joint distribution over these types. So you can, in other words, think about the expected total virtual valuation. That could be one way to describe this integral formula. So since this is the expression for the total revenue earned by this mechanism designer, we can write this optimal mechanism design problem to be the one which maximizes this value subject to the condition that f is non-decreasing in expectation. So this is a necessary condition. Again, once we have fixed the allocation rule, the payments are already fixed. So therefore all that we really want to optimize is over f, but f should satisfy this non-decreasing in expectation property in order to make this mechanism Bayesian incentive compatible. So as before, we are going to solve this problem ignoring this constraint. So suppose this constraint did not exist, then what would have been the right thing to do? So of course, if WITI were negative for all these players, then very naturally if IT should also be 0 for all these players. That means the object is unsolved. That is the optimal mechanism. But if there was at least one WITI which was positive, so then we could have allocated the object to the one whose virtual valuation is the highest. So we look at, so in this type profile, we look at which of these agents have the highest virtual valuation and allocate that object to that agent, and for all the other agents, and the allocation is 0. So in this setting, it is solved. Now the natural thing is that even though this is an optimal solution of this optimization problem in the unconstrained domain, this f could be a function which is non-NDE. So in order to find an example, you can look at the original paper by Meyerson, 1981. So the title of the paper is Optimal Auction Design. Essentially all the results that we have discussed in the context of optimal mechanism or selling the single object is actually from this paper. But the idea of this example, to construct an example which is not NDE yet satisfies this the unconstrained problem, is that the following condition that we are going to define of regularity is going to get violated. So let us come to the regularity condition and see how you can construct an example of FIT which violates that condition but still can satisfy this condition 1. So in general, this paper, this should be a must-read paper if you are really interested in understanding more about optimal auction design. So the virtual valuation, we are going to define a virtual valuation to be regular if it is strictly increasing in its arguments. So look at two different SI and TI, where SI is smaller than TI, then the virtual valuation should also be following the same direction. So WISI should be less than WI of TI. If that holds, then it is going to be regular. One remark is that this condition is actually weaker than MHR condition. So it is very easy to show that if the functions G or GI, so if GI satisfies MHR, then it implies that the corresponding WI is regular. So since it implies the regularity condition, quite naturally this is a less restrictive. The MHR so the regularity condition is a weaker condition than MHR condition. So now we are going to assume from now on that the agent's valuations, the virtual valuations, are all regular. So the allocation rule, if we assume that property, that it is regular, then the allocation rule of the optimal mechanism is the same as the solution of the unconstrained problem. So now you see that if that regularity condition is violated, then you can actually construct one allocation rule, Fi of t, which violates the regularity condition yet can satisfy this condition. And we are also not going to get into the details of this proof. It's quite obvious. So the solution of this unconstrained problem is given by this equation of 1. And what regularity ensures is that whenever you have some Ti which is larger than Si, WITI is always going to be larger. Now because regularity is satisfied, then the optimal allocation rule also should satisfy this condition. Why is that true? Because of the construction of Fi of t. you can see that whenever you have, so let's say we consider two different type profiles, fi of ti t minus I, and another type profile which is si t minus I, and si is smaller than ti. So this is always going to allocate the object to the agent whose virtual valuation is the highest. And because there are so if there exist two different types, so si whose virtual valuation is the highest among all the other players, then that at that allocation it is going to be allocated. But here because ti is even larger than that, its virtual valuation is always going to be larger than that. Therefore that agent will continue getting that object. So if an agent gets the object at a type which is si, then it will get the object at any higher type, given that the type of the other players are held fixed. So this is by the construction of this allocation rule, and therefore it satisfies not only non-decreasingness in expectation, it satisfies the non-decreasingness. So by construction of this mechanism fi under the regularity condition, we can ensure that this fi satisfies non-decreasingness, and therefore it is of course non-decreasing in expectation. So therefore this rule fi is BIC. So what we have under this regularity condition, we have actually solved this optimization problem, which is the optimal mechanism design problem. We have constructed an f which is non-decreasing in expectation and also maximizes this. And the mechanism is really very simple. You just order all these players with respect to their virtual valuations, allocate the object to the individual whose virtual valuation is the highest, and the payment will be given by the standard integral formula which we have already discussed before.